Today I want to start off with compare. So till now what we have looked at is basically how to design, I mean what are the different architectures, right? What are the different ADC architectures, and in all of them we have seen that the comparator is at the very heart of the design. So if your comparator is screwed, the whole thing is screwed, right? So comparator design. So how do we build a comparator? So any idea? Can you give some suggestions? So we know what is a comparator? The basics of a comparator. So let's say this is VP, VM, and Vout, right? So if VP is greater than VM, you have a Vout of VDD, and VM greater than VP, you will have Vout equal to ground, right? And let's say this also is going to be a clocked comparator. Okay. So how do you think we can implement a comparator? Can you think about it? So how can we get this functionality? So forget about the clock. Let's worry about the clock later. Now, how do you think this kind of a transfer function or this kind of a behavior can be obtained?
Using op amp.
Okay, to be more precise, so how can you? I mean, what is the functionality? Like, what are you going to do? You have VP and VM. Let's say VP and VM are separated by a few millivolts, or let's say few tens of microvolts, a few hundreds of microvolts, something like that. For example, let's say your VREF is 1 volt, and let's say you have a 12-bit converter. So what is your LSB size? It's going to be 1 divided by 2 to the power of 12 volts, right? So what is that value? 1 divided by 2 to the power of 12. That happens to be 244 microvolts, okay, approximately, right? So which means that your comparator's accuracy should be less than even half your LSB, right? Or even quarter your LSB, let's say. So let's say you want your comparator to be able to discern between two signals which are at, let's say, for example, 50 microvolt. What can you do? What is the functionality that is here?
It is VDD and ground.
Can you repeat? Your voice was breaking. Can you repeat once again?
It is reaching either VDD and ground.
Put a switch between VDD and ground? No, I didn't get you. Yeah, of course, Vout will basically be driven by an inverter. I mean, that is fine. I mean, the question is, let's say VP, let me give you an example. Let's say 600.03 millivolt, okay, and VM is 600 point, sorry, not 600, let's say 599.97 millivolt, okay. What is the difference between these two voltages?
.06.
Correct. It is 60 microvolt, okay. Now, these are the two inputs. The output should be what? What should be the output?
Amplified.
VDD, right?
Yeah.
Now, how can you get this? It's okay. I mean, you can guess, you can think of something. Somebody said op amp. Like, what will you do with the op amp? Let me ask you that question. What will you do with the op amp?
We make a differentiator, means subtract VP minus VM, and
Yeah,
then
that's an op amp
That's the
anyway will
difference.
do VP minus VM, right? Like, okay, if you subtract it, you get 60 microvolt. Now, how do you come from plus 60 microvolt to VDD? So you're saying directly use an op amp. That's what you're saying.
It has its open loop gain, so it might.
But
Okay.
the
So okay,
open loop,
fine. So
yeah,
okay,
open loop gain might not be enough to amplify it to VDD
correct.
60 microvolt.
Right. So for example, if the open loop gain of the op amp is 60 dB, which is what some of you had designed for last class, that is basically 1000, right? So if you multiply with 1000, what will happen? So 60 microvolt into 1000 becomes 60 millivolt. Correct. Some of you designed 70 dB op amp, so that becomes some 180 millivolt or something, right?
So then we use PMOS or NMOS depending upon the in the output of the open we can use PMOS or NMOS.
If you put a
Okay.
PMOS, what will happen?
If we then sir, one second sir, if we put
I mean, then okay. The other scenario can be that these two are interchanged. What will happen? You need to go to ground, right? So if you
yes
take
sir.
3 millivolt and give it to a PMOS and connect it to VDD and the output is connected to that, it will be always on, always VDD, unless your input swing has become larger, right? So in other words, what is required is, we can basically say we require a very large amount of gain. Can we say that? Let's say I bring in another op amp of 60 dB. Okay, this becomes 60 volts, which is not possible. Basically, it will go and, let's say if I bring in another op amp which has a gain of 200, what will happen? 6000 millivolts or 6 volt. So it will anyway raid, right? So if you put 10, it becomes 200. Let's say if I have a gain of 20, right? If I have a total gain of 20,000, this input will go to 1.2 volt or ground, right? So basically, we can just say that it needs a very large amount of gain, and the lower the resolution, the larger the amount of gain. Now, we all know that if you start putting op amps in series, I mean in cascade, right? So one of the problems is that the op amp gain, open loop gain itself, will vary with process voltage and temperature, right? So you will have to kind of go and do a lot of over design. Well, some cases when you really need, some amount of gain, you can basically do that. But if you want to really have a very large amount of gain, right? What you can do is, instead of putting multiple gain, see, if you put multiple gain elements in series, in cascade, there will also be some parasitic feedback paths, right? And those feedback paths will go and start, what will they do? I mean, it can cause instability. Okay. Now, more important than that is that your open loop bandwidth, 3 dB bandwidth, is very small, right? Your open loop 3 dB bandwidth is very small, right? And therefore, let's say if your gain bandwidth product was okay, let's say your open loop gain was UGF is 200 megahertz, right? And if your open loop gain is 1000, okay, your 3 dB bandwidth of open loop is what? 200 megahertz, or let's say it's 100 megahertz. You'll basically have 0.1 megahertz, which is 100 hertz. Now, you can, and the moment you put these op amps in series, in cascade, you will have even lower bandwidth, because it becomes a multipole system now. Okay, so your bandwidth becomes very limited. Your comparator cannot operate at higher speeds. Okay, so in order to solve all these issues, we are going to use positive feedback. Okay. Now, how can we use positive feedback? First, let us start off with a block diagram type approach, and then let us build on. I mean, then we can bring in circuits and we can fill up the gap. Okay. So what I'm going to start off with is a transconductor. It's a GM. We all know how to build GM cells, right? An OTA. Okay. So it has some plus and a minus terminal. Right now, what I'm going to do is I'm just going to do it as a block diagram thing. Okay. Let's say Vin is the difference signal. Okay. What is the difference signal? Basically, this Vp minus Vm. Okay. Now I'm going to take the output, feed it back in, and let's say there is a capacitor C. All right. I mean, you can't label it as two nodes. Let's just call it as this node as V. Okay. So you have a transconductor where somehow, let's say magically, because now we are only talking about block diagrams, so then later we'll figure out how to do all these things properly. Or let me show you how exactly it is done also. Okay. Let's say you have a switch. This is your V in. Let's call this node as V. Okay. At a certain instant of time, you connect it. You store that value of V in, or rather this Vd, on this capacitor. Okay. So at, let's say, before t equal to 0, t less than 0, switch is closed, and V is equal to Vn. Okay, that is the voltage that is stored on the capacitor. Let's say this is Vd, which is equal to Vp minus Vm. Okay, let's assume that somehow we are able to find out this voltage and put it there. Okay, and it can be a very tiny voltage. Now at t equal to 0, switch is opened. All right, and let me also put one more switch. Okay, let me call it S1, let me call it S2. Switch S1 is closed, S2 is open. Here I will say S1 is open and S2 is closed. Understood? Okay. So here, now what will happen? Okay. So let's try to understand. So t less than 0, you had Vin connected to this capacitor, connected to this transconductance cell, which is not connected, which is the feedback is removed. For t greater than or equal to 0, you have only this capacitor, okay, and V of 0 is, let's say, Vin, and that is given to this transconductor, which is now connected in feedback. Okay, and we are interested to find out what is this V of t. Okay, so what does a transconductor do? It looks at a certain voltage and generates a certain amount of current. So the current which is produced by this transconductor, let's call it I. Okay, this I can be written as what? I can be written as Gm times V, right? And what is this V? Or rather, what is this current? How is this current and this voltage related? There's some current flowing into some capacitor. So we know that this is given by C dV by dt. Correct? So far it's simple, elementary. Now let us rearrange the terms a little bit. So let's say we have on one side dV by V is equal to Gm by C into dt. Correct? Same equation rewritten. Now let us integrate on both sides. Integrating, what will you get? Gm by C into T is equal to, what is the integration of dV by V?
ln log V.
Ln of V.
V.
Okay, plus some constant. Okay, plus some K. So what happens is, this, if you solve the equation, how will you get? You'll basically get the form V of t is given by V naught into V naught being V of 0 into 1 minus e power minus t by, or rather plus V into e power plus t by tau. V of 0 into e to the power of, when t equal to 0, right, the voltage is basically V of 0, right? So you will basically get that. So it will be written as e to the power of t by some tau, where tau is given by C by Gm. Now, if you look at this expression, right? In fact, what you will do is like you will say, okay, this can be written as ln of V of 0, right? And so basically you'll get V by V into V naught. So V by V naught rather, and then you will get this expression. So whatever. So now this is not e power minus t by tau. It is an exponentially growing function, right? So I rewrite this equation V of t given as V of 0 e power t by tau. This is an exponentially growing function, correct? So which means that as you give it to, if you, let's say our V of 0 is this small 60 microvolt, okay? Now if you wait for some amount of time, what will happen? If you plot this, let's say V of t, let's say V of 0, okay, it's going to basically go as an exponential, an exponential function. Now what is our requirement? We want to know how much time we need to wait till this voltage reaches what value?
VDD.
VDD, correct? So let's say this is VDD. So how much time you need to wait? So we basically have, let's call it as T, capital T1, okay? So at T equal to capital T1, V of t becomes VDD. So then what happens? So we want to find the time. So it becomes VDD is equal to V of 0 e to the power of t by tau. This can be written as t is equal to tau times natural logarithm of VDD by V of 0, correct? And this is nothing but T1. Now what can we infer from this? One thing is, higher the tau, okay, in other words, if your C by Gm is higher, you will have slower conversion or slower comparison, let's call it, okay. So which means that you need to make sure that C by Gm is low, or in other words, Gm by C is high, correct? Now what is the other thing? As V of 0 increases, T1 also increases, correct? So which means that as you try to discern or distinguish between smaller and smaller voltages, the time required for your comparator to successfully do a comparison increases, okay, and there is a logarithmic relationship here, correct? So in other words, the smaller the voltage, okay, let me write it here, smaller the voltage or smaller the VD, which is given by Vp minus Vm, the larger the time taken, okay. Now we cannot arbitrarily wait for a very long period of time, correct? So for example, if your sampling rate or is forget about sampling rate, let's say your clock frequency, right? All these things are usually clocked, right? Even here I have put about, I used clocks here, right, to control the two switches, okay. The clock frequency is a certain amount. Now for example, let's say you want to have a 1 megahertz conversion, okay. Now if you're not one, let's say the comparator is working at 1 megahertz. So here we have two phases, right? One phase to write the voltage to the capacitor, another phase for this positive feedback to happen, right? Now if you assume a 50% duty cycle, then how much time do you have? T comparator, what is the time for comparison? What is the time for regeneration? Let me just put T reg for regeneration. Okay, regenerative comparator as it is called. What is the time? So 1 megahertz means time period is 1 microsecond, right? 1 10 power 6, 10 power minus 6, it is 1 microsecond. Half of that is 0.5 microsecond. Okay. In other words, what we are telling is, see, boss, I can wait only for half a microsecond. Okay. If you can differentiate, I mean, if you can amplify this voltage to something which is close to the supply rails, I am happy. If not, I cannot do. Correct. You cannot say, please wait, I have not yet, fully done the comparison, right? There is a clock and it's going to work. Either you are able to successfully do the comparison or you are not able to successfully do the comparison. Correct. That is how it works. So in other words, if I were to plot VD here, the difference voltage, okay, let's say this is absolute 0, okay, and on the y-axis, I am going to plot, the time for comparison. Okay, how do you think the graph will be? For very large differential voltages, the time for comparison is very small, correct? And we saw that there is a kind of, what was it?
Bell shaped.
Yes, it's asymptotically bell shaped. Okay, so it basically it's a logarithmic curve, right? So okay, so it is going to be asymptotic. It will never reach a certain point. That is the whole point, right? If you look at this equation, if you go to, instead of let's say 60 microvolt, you are going for 60 nanovolt. Then let's say you are going to 60 picovolt or 1 femtovolt. Okay, as you keep reducing the voltage, I mean, exponentially the time taken for you to reach VDD is going to grow up exponentially. Okay, so
In the previous slide,
yeah,
I think this T1 should decrease as you've written V0 increases. In the
as V0 increases, T1 decreases.
you have written, I think, increases in the left corner.
Oh, okay. Sorry. Yeah.
Yes.
Thanks for pointing it out. Okay. Yeah.
Yes.
So basically, there is no convergence point. It asymptotically goes up. Okay. So we know that we cannot wait infinitely. So we are going to say, okay, I am going to draw a line here. Let's say my T comparison is only, this is my T, right? Okay. Then what happens? It means that you can successfully detect only this and beyond. Okay. Now this is what is called as metastability. I think you would have studied metastability in your. Have you studied metastability in when it comes to latches, flip flops?
Yes, sir.
Right. So have you seen a curve which is like this?
No.
No.
So
Okay.
when two inverters are connected in cascade, then the curve it's similar but not exactly this.
Yeah, good man. You basically, that's the implementation. Okay.
Yes.
All right. So this is the block diagram type of thing to first understand the performance. The implementation is basically a back-to-back converted inverter. All right. That's it. Okay. So there is what is called as metastability. So this is your metastable region. So what is metastable region? There is no proper decision taken. Right. Now, instead of saying 1.2 volt, you can always say, in digital systems, you say VIH and VIL. What is VIH, VIL? What is VIH for an inverter? the minimum voltage that is considered to be a logic high, right? I think you would have studied it, right? So if you say a 1.2 volt system or let's say 3.3 volt system, I mean, what is considered as logic high need not be exactly equal to 1.2 volt. Okay. So for example, for a 1.2 volt system, anything greater than 0.75 can be thought of as a, I mean, the system, your circuit can very safely interpret it as being logic high. Anything lower than let's say 0.3 volts can be safely interpreted as a logic low. Okay. So, so instead of giving 1.2 volt, you can always give that VIH or VIL, which is the tolerance of your logic voltage levels, right? And you can say what is the metastability time. Okay. So, or the metastability region. So, when you are designing an inverter, a comparator, let's say you have, for example, this 12-bit example, you want to be able to easily distinguish, let's say, half your LSB. So that will be what? 122 microvolt. You have to make sure that your comparator has a metastable region which is within that 122 millivolt. Okay. That is to say that 122 millivolt, microvolt does not fall within your metastable region, even across PVT, process variation, temperature variation, voltage variation. Okay. So that's very important to ensure. Okay. Now, as who was it, Sarath, or was it who gave the thing about back-to-back inverters?
It's me, sir, Ankit.
Ankit. Oh, okay. Yeah, sorry, I'm not able to differentiate the voices. Okay. Yeah, correct. Very good. So basically, you have back-to-back inverter. That is basically your comparator. Okay. So the actual thing, let me just conclude the class with that today. Inverter, you have two inverters. Right. And let's say you have, instead of writing a VD, you can always say, let's say this is pi, this is pi, and then you can, and this is, let's say, pi bar. Okay. So in the pi phase, you are writing the inputs. Okay. And in the pi bar phase, you are basically, it's the regeneration phase. Okay. Now, of course, you can always have a reset phase and so on, right? Just to get rid of memory effects and so on. And an inverter, when connected back to back, basically it will act as this thing. Of course, this is a very elementary, this is a latch and is a very elementary comparator. This will basically work as a comparator. Okay. Of course, you might put some, inverters to kind of take the bit and bit bar. All right. So now, but there is what is called as a strong arm latch. So we will look at it in next class. Okay. So that is what is very, very widely used as a comparator in the industry. In fact, this is also used as sense amplifiers in memory circuits. Right. I hope you have come across this in SRAMs, DRAMs. Right. Even in these big memory arrays, when you give your bit line, word line and bit line, the bit line will shift by very small amount, by maybe a few millivolts. And your sense amplifier should be capable of looking at the difference between the bit and the bit bar and be able to resolve it into a logic high or a logic low. So in sense amplifiers, you basically use something very similar. Okay. And some peripheral circuitry which is around it will keep changing from implementation to implementation. But pretty much, if you look at clock comparators, at the heart of it, you have cross-coupled inverters. Okay. And strong arm latch is something that is very widely used. We'll see what are the small things which are available around it. Okay. Any doubts? Any questions? Okay. All right. So let's wind up class with this, and let's meet on Monday. Thank you.
Thank you.